A very good morning. Welcome back to my YouTube session. Today's subject is physics, and we're going to learn a very interesting topic in physics, that is applications of quantum mechanics in the field of quantum computing. So, you all know me by now. I'm Liana Rose Francis, studying in Sri Venkateswara College of Engineering, doing my BE in CSE Cybersecurity. So, let's start today's session. So before talking about the applications of quantum mechanics, let's learn what is quantum mechanics. Quantum mechanics is a subfield of physics that describes the behavior of particles, atoms, electrons, photons, and almost everything in the molecular and submolecular real. Developed during the first half of the 20th century, the results of quantum mechanics are often extremely strange and counterintuitive. It is the foundation of all quantum physics, which includes quantum chemistry, quantum field theory, quantum technology, and quantum information science. Now, discussing more about quantum mechanics, it can describe many systems that is classical physics cannot. Classical physics can describe many aspects of nature at an ordinary, that is macroscopic and optical microscopic scale, but is not sufficient for describing them at very submicroscopic, atomic, and subatomic scales. Most theory in classical physics can be derived from quantum mechanics as an approximation valid at large, macroscopic or microscopic scale. Quantum systems have bond states that are quantized to discrete values of energy, momentum, angular momentum. The other quantities, in contrast to classical systems where these quantities can be measured continuously. Measurements of quantum systems show characteristics of both particles and waves. Wave-particle duality, and there are limits to how accurately the value of a physical quantity can be predicted prior to its measurement, given a complete set of initial conditions, the uncertainty principle. That is the Heisenberg's uncertainty principle. So all these people in this photo are the main people who contributed to this quantum mechanics. So quantum mechanics arose gradually from theories to explain observations that could not be reconciled with classical physics, such as Max Planck's solution in 1900 to the black body radiation problem and the corresponding between energy and frequency in Albert Einstein's 1905 paper, which explained the photoelectric effects. So these early attempts to understand the microscopic phenomena now known as the old quantum theory led to the full development of the quantum mechanics in the mid 1920s by Niels Bohr. He took both the ideas from Albert Einstein and Max Planck and he gave the quantum mechanics formula. Now, Erwin Schrödinger and Werner Heisenberg also involved into this, Max Born and Paul Dirac and others. The modern theory is formulated in various specially developed mathematical formalisms. In one of them, the mathematical entity called a wave function in the form of probability amplitudes about what measurements particles' energy, momentum, and other physical properties may yield. Coming to the applications of quantum mechanics, first one, lasers. It's used in very sharp, highly defined lasers. It is used to cut in any hard materials, also used to penetrate through the body parts. Solar cell, it is used in electron microscope. It is used also in cryptography, microscopy, medical imaging, and MRI scanners. It is used in fluorescence bulb and phosphofluorescence, atomic clocks, holography, quantum computing, magnetic resonance, imaging, transistors, GPS, television, and so on and so forth. These are the applications of quantum mechanics. Now, dealing with the topic of today's session is quantum computing, which is the application of quantum mechanics. So it uses a very specialized technology, including computer hardware and algorithms that take advantage of quantum mechanics to solve complex problems that class computers or supercomputers can't solve or can't solve quickly enough. So these solve very quickly enough, and they are very useful for big companies such as IBM, Google, and etc. The field of quantum computing includes hardware research and application development. Quantum computers are able to solve certain types of problems faster than classical computers by taking advantage of quantum mechanical effects such as superposition and quantum interference. Some applications where quantum computers can provide such a speed boost include machine learning, optimization, and simulation of physical systems. Eventual use cases could be portfolio optimization in finance or the simulation of chemical systems, solving problems that are currently impossible for even the most powerful supercomputers on the market. So the advantage of quantum computing is no quantum computer can perform a useful task faster, cheaper, or more efficiently than a classical computer. Quantum advantage is the threshold where we have built a quantum system that can perform operations that the best possible classical computer cannot simulate in any kind of reasonable time. Now let's talk where quantum computing is mostly used in all these companies. So let us see how they use this quantum computing. So this quantum computing can revolutionize industries. So examples for this is first one is machine learning. So machine learning is the process of analyzing vast quantities of data to help computers make better predictions and decisions. Research in quantum computing studies the physical limits of information processing and is breaking new ground in fundamental physics. This research leads to advances in many fields of science and industries, such as chemistry, optimization, and molecular simulation. It is also a growing area of interest for financial services to predict market movements and for manufacturing to improve operations. Let's go to the optimization. Quantum computing can improve research and development, supply chain optimization, and production. For example, you can apply quantum computing to decrease manufacturing processes related and shorten cycle times by optimizing elements such as path planning and complex processes. Now, another application is the quantum of optimization of a loan portfolio so that lenders can free up to capital, lower interest, and improve their offerings. Talking about simulation, the computation effort required to simulate systems accurately scales exponentially with the complexity of drug molecules and materials. Even using approximation methods, current supercomputers cannot achieve the level of accuracy that these simulations demand. Quantum computation has the potential to solve some of the most challenging computation problems facing chemistry, allowing the scientific community to do chemical simulations that are intraceable today. For example, Pascal built their Quebec computational software to run chemistry simulations. Quebec automates the heavy lifting necessary to run quantum computation tasks, from automatic provisioning of the computing infrastructure to running pre and post processing classical calculations and performing error mitigation tasks. So this is a supercomputer that is developed by the IBM company from Germany. Now let's talk about the applications of quantum computing. So first one, it is used in artificial intelligence, better batteries, cleaner fertilization, cybersecurity, drug development, electronic materials discovery, financial modeling, solar capture, traffic optimization, and weather forecasting and climate change. And there are so many other applications of quantum computing. So these are the few main applications of quantum computing. We have come to the end of the slide. Thank you for bearing with me and for listening to this session. Please do like, share, and subscribe, and have a nice day.